So the topic today is how we can basically go from our laptop to our supercomputer with AI. So the assumption here is that most people here are interested in AI, and we're going to talk a little bit about the background of some of the compute resources that are available in Germany, a little bit in Europe as well. But today the focus is, of course, resources from Germany, namely the GCS and those available from the NHR. And so, without further ado, we can get right into those topics. So, the first thing is to introduce this so-called HPC landscapes in Germany. It's this tier system. So, in this pyramid here, you see roughly from the top, the tiers go from 0, 1, all the way down to 3. And the lower the number, or the higher the point in the pyramid you are, these are the larger the resources and available to more parts of Germany and Europe. So, at the top, we have tier 0, which consists of this Euro HPC joint undertaking, which was founded in 2018, and basically it's a bunch of EU countries and private partners that offer HPC services for very large projects across Europe. If we go down one tier or to the next tier, let's say getting more local, we can talk about the GCS, which is the Gauss Centre for Supercomputing. So they support HPC projects and research in Germany and also offer some partial support for these larger Euro HPC projects as sites for these resources. And then we go down to a little bit of an even more local tier or smaller resource tier, and this is the NHR tier. And so these institutions, which form a network of 9 institutions across Germany, allow access for mostly university researchers to HPC resources free of charge, provided that you have some application that you fill out to be able to use these resources. And we'll talk a little bit about this later. But these largely support German universities and their HPC needs. And then below this, we have the so-called Tier 3, which basically supports or is consisting of the local systems that are available as part of universities themselves. So these are the HPC systems that are run by, say, the physics, computer science, or chemistry departments of German universities. The most important thing is that at all of these levels, so going from Tier 0 all the way to Tier 3, there is funding available and has been provisioned for the use of powerful HPC systems that are perfectly suitable for scaling up AI workloads to tackle some big problems in research. So, first, we get a little bit more information about the two important tiers that we're going to talk about today. So, we're not going to focus so much on your HPC, but more on these local solutions that are offered in Germany. And this is, of course, the GCS and the NHR. So, as mentioned before, the GCS is the Gauss Centre for Supercomputing. It has the 3 largest HPC systems in Germany as part of the Tier 1 group. And as mentioned before, the access is primarily aimed at researchers from Germany, but there is also some partial support from other researchers from other European Union nations through this Euro HPC joint undertaking. So Gauss Center for Supercomputing also hosts resources for some of these external researchers as well. And of course, we have the NHR, which, as I mentioned before, consists of 9 HPC centers that are located in Germany. And these comprise the tier 2 of the pyramid that we just discussed. And primarily, the access is aimed at researchers from German universities. In addition to access to these resources, we also offer some additional services. The first is the consulting from NHR staff. So if you have a particular domain that you would like to work or incorporate AI into, or some sort of, it's not only for AI, but today we talk about AI. If you want to incorporate this in your research for a specific domain, you have access to experts that are working as consultants as part of these NHR centers that can help you debug your problems, design research projects, and do anything from simple as, I don't know why my script is not working, or I'm getting this strange error when I run into this, all the way up to our discussions through weekly cafes and other offerings that we offer, which we'll again advertise later, for questions about just general AI topics on HPC. And of course, there's also the NHR Graduate School, which helps to promote young scientists that are interested in getting into research and building careers in research based on high performance computing. And of course, I have to mention that both the GCS and NHR centers have large GPU clusters, which we'll talk about in a little bit, that are really suitable for AI training and inference that allows you to scale up your research to solve very, very big problems that have, let's say, important academic or industrial industrial impact. So first, just a little bit more information about GCS. So, a bit of the offering that we have here, you can see that there are multiple different types of hardware that you can use. So, there's these hardware that's available in Stuttgart. So this is the HPC Cray systems, as well as some APUs that are available there with some large memory capacity. At Jülich, you have a few different clusters, and these also offer lots of GPUs, both the A100 and the newer NVIDIA H100s, also some fairly large memory GPUs there. And then there's also some resources that are additionally available at the Leibniz Supercomputing Center. Namely, these are not NVIDIA GPUs, but the Intel Ponte Vecchio GPUs, which are somewhat of Intel's competitor to this A100 card that's available at many centers from NVIDIA. And we'll talk a little bit more about the resources specific to NHR in a later, because there are more centers and a bit more difference in terms of the resources that we offer. But before we talk about that, we have to, of course, introduce what we mean by HPC system. So if you're new to HPC systems, or if you just do AI work on your laptop or on your local desktop or something like this, this is some important background information for you. So an HPC system is essentially just a collection of many computers that are stored together in a room or in a cluster like this that you see in the picture here. So this is one of the HPC clusters from Karlsruhe, which is a participating member in the NHR. Basically, the idea is that if you want to solve very large problems, maybe you want to run a very large simulation for a climate modeling, or maybe you want to run a very large simulation of a very big protein or molecule in water, this probably could be done technically on your local computer or your laptop, but it would take a very long time because you just don't have the processing power and the hardware that's able to scale these up. And the way that this is scaled up is it takes your problem and it distributes it in multiple different ways, but there's more information about that later. But the idea is that it takes a very big problem, breaks it up, and distributes it among many computers so that each computer, or each node in this case, is solving a smaller subset of the problem. And then all together in concert, these computers are able to talk to each other through a local network and a shared file system, and they solve this big problem in concert in a much more efficient and faster time than it would take if you just were solving it on your laptop or your local hardware. And so what we mean by this smallest unit of the HPC cluster is the node. And you could think of the node as basically just a computer. So in the same way that a computer has RAM, CPU, and GPUs and other hardwares, this is basically what we call a node. So nodes can have many different parts to them, but I think it's simple to think of them as basically just a computer. You have some RAM, you have a CPU with many, possibly many different cores inside. It has a file system that's available to the computer. Also, it may have additional hardware like GPUs, which are of course very important for AI workloads. And it has a way to communicate with other computers connected to the same network within the same cluster. And this is the network interconnects that we mentioned previously. So within an HPC system, the nodes can be specialized for different tasks. So usually these are called partitions. And the idea is that a partition may have a collection of nodes, and this is what forms a cluster. And within a CPU partition, for example, you may have a bunch of nodes that are suited for CPU tasks. So maybe classical simulation tasks or classical climate simulation jobs. These are very CPU using codes. Within a partition, you may have nodes that are specialized for the computation, meaning that most of the computation takes place on those nodes. You may have specialized nodes called login nodes, where you prepare your job, you download your data, you format your data set, and get it ready to send to the computational nodes. And you may have nodes that have very special capabilities, such as those with high memory, or if you have another AI partition or something like this, maybe those nodes have special hardware like GPUs. So in this example on the right, you can see that there are several nodes that have A100 GPUs on them, or H100 on them as well. And the idea is that all of these are connected in a way such that ideally they have access to a shared file system, so that all of these nodes are able to read data from the same place, read and write, that is. And the idea is that, okay, we have all these computers and we have them at our disposal. They're organized within a partition and they have a bunch of nodes that can all do specific tasks. How do we actually use them? Well, this is where we introduce the concept of the high performance computing job or HPC job. And a job is a vague concept. There are many more specifics you can talk about depending on your scheduling system, which we'll mention in a bit. But the idea of a job is that with your problem that you want to solve, you need to identify the following things. This is not an exhaustive list, but just some important examples. So let's say I'm ready to run a simulation, or I want to run a training of an AI model that's very big or has a very large data set. I need to know beforehand or specify for my job the number of nodes that I want my job to run on. Maybe I need to give some information about how many tasks per node needs to be done. So maybe this is a way to specify how many CPU cores you want to use. You need to specify the partition that you want to run your job on. Some partitions have certain resources and others don't. For example, a GPU partition versus a CPU partition. And you also need to specify things like the time that your job expected to run, the memory requirements of your job, how many GPUs per node that you want. If you are running your job as part of a project account, you need to specify this information, and this can be discussed later when we talk about how to establish and set up these project and test accounts at the NHR. But the idea is that as the user, you basically just need to know a little bit about the resource demands of your job, and you specify these in what's called a job file. And this is what's sent to the compute nodes, and this is how your job runs. Your job runs, and then the results are combined together and then sent back to you for analysis. You can do that off-site, or you can run another job to analyze your data as well. And in practice, this is the way that it works. So you have your laptop or your local desktop computer. You typically get access to an HPC system by applying for an account or a project account or a test account. And then you SSH into the front end or the login nodes. So these are specialized nodes that are not meant for computation, but are meant to help you submit jobs and also prepare your data so that the jobs can run correctly and smoothly on the compute nodes. Once you submit your job, usually this job is managed by a workload manager or a scheduler. A popular one that is used at many of the systems in the NHR is called Slurm. And the idea is that there are many researchers who are also applying to use these resources and submit jobs to them too. So there's a big queue of jobs, and the scheduler manages whose job gets sent to the nodes next. If your job fails, the scheduler will send it back to you with an error. You can also monitor and track when your job is expected to begin, or if your job is delayed or stuck for a certain reason. Maybe there's something that you specified incorrectly. So the scheduler helps you to interface with the compute nodes by managing the jobs that you submit. And the idea is that once you are waiting in the queue, your job floats to the top based off of priority and a few other variables. And this is also something that is maintained and set by each HPC cluster or the admins that are taking control of this. And your job floats to the top of the queue, and when it's your turn, it's sent to the supercomputer, the compute nodes. It runs, hopefully, correctly, and then it's sent back to you, and you can decide what you want to do from there. If you want to analyze your data or run another job, this is basically up to you and your specific research problem. And to give you an example of how to submit this for something like maybe an AI training project. So let's say you want to train an AI model using Python. Maybe you're using PyTorch or JAX or TensorFlow. And the idea is that, at least for Slurm, this is an example of how one would use the Slurm scheduling system to submit their jobs. Again, you need to specify the resources that you want. In here, in the case of Slurm, these are these S-batch commands that are given in green. So you specify the number of tasks, the number of nodes that you need, special resources that you need, like GPUs. So in this case, they're asking for 4 GPUs on 2 different nodes. So that's 8 GPUs in total because there are 4 GPUs per node. You give a time, you give a partition that you want. Maybe there's certain partitions that have certain GPUs that you like. Maybe you prefer Intel or NVIDIA, etc. And if you're part of a compute project at one of these NHR sites, then you specify your account so that your computing time is tracked and you don't exceed what is allocated to you. And then you may be able to load some local software that's been provided by the consultants or the admins of these centers. So let's say you need some GCC tools or you need PyTorch or OpenMPI. And then maybe you want to activate your local environment. If you use Conda or Mamba, you can also deploy and manage your environments on these HPC clusters as well. And then finally, you can use an srun command. So srun is a parallel job manager built within Slurm. But this is a way to basically send your training script. Maybe you have some training script that you've written called train.py. You pass it some data or some other command line flags or something that you've written yourself. But the idea is that you can see that in order to go from really just the one line at the bottom that you would normally run on your laptop or your local computer, starting with this Python statement here, in order to scale this problem up to take advantage of these resources and do your research much more efficiently, you really only need to add a few more information, and you can build these AI workflows that you're comfortable with and happy with on your laptop and your local computer, and just add a little bit of information so that the scheduler is able to send this to the nodes for the compute time that you've been allocated. And it's really not much work. That is to say that if you're used to doing something a certain way with your AI workflows and pipelines on your local computer, in order to take advantage of the HPC resources that are available through the NHR and GCS, you just have to add a little bit on top of your workflow, and it's quite easy to get up and running. And so we'll talk about a little bit more of these examples as we go through the remainder of the talks. But this is the summary of what we mean by an HPC system. And I'm happy now to move on and give the control of the presentation to the next presenter to talk about some of these more topics in detail.
So in the next section, as I mentioned, I would like to go a little bit more into detail into how to use the HPC resources available in our systems. And from that, let's have a look at the perspective that some of you might have. So, and that, yeah, a quite larger number of people in the AI community have, and that's why we're doing this webinar, is namely that they're currently using their laptops or desktop computers, some workstation that might have like of the order of 1 or 2 GPUs maybe, and a few hundred gigabytes to like smaller number of terabytes of main memory. If you, in contrast, look at our HPC systems, for example, here the UWITS supercomputer in Jülich or the Nocta 2 system here in Paderborn, we have of the order of a few hundreds to a few thousand GPUs and storage in terms in the sizes of a few thousand terabytes or petabytes to like 50 to 100 petabyte range. And that way you can see that from your local resources, be it your workstation or your laptop, scale up by a factor of 100 to like factor of 10,000 of what is available on these HPC systems. And you can then hopefully also understand why we need this kind of scheduler to make good use of these HPC systems and to make them available to multiple users. So to move on from the laptop or workstation, when you come into the situation of needing more resources, depends on the use case. So as I mentioned, usually you start your AI and machine learning work on your laptop workstation or on a very small cluster. And then you come usually to the situation that you want to do longer computations, longer trainings. You want to use more data sets, larger data sets, or just plain need more powerful GPUs to do the things. And then one way of using these our HPC systems is not directly going to Slurm jobs, as Nick showed you, but to use, for example, the Jupyter Hub services that we have. Because you might already be familiar with using Jupyter Hub and Jupyter notebooks on your local computer for doing your AI research. And we directly also offer Jupyter Hub and Jupyter notebooks on our HPC systems, where these notebooks actually run on compute nodes in our HPC clusters so that you can use all the resources that are available in our HPC systems, like GPUs, like fast storage, large storage, and so on. So the advantages of that is that you can do in the same way that you would do on your laptop, for example, in the Jupyter notebook, use the resources interactively. instead, you now have more resources because you have more powerful GPUs available, larger and faster storage, and also nodes with multiple GPUs, for example, 8 GPUs or 4 GPUs that you can use at the same time. And if you want to, you can also do multi-node jobs and run these Jupyter notebooks not just in one node, but on multiple nodes in parallel. This is all then, as you're used to in Jupyter notebooks, available just from your web browser, and you can use Python and Julia in these notebooks. So most of the HPC systems offer this kind of services, and usually we recommend them to get started so that you have an easier way of transitioning from an interactive use on your laptop or workstation to using the HPC resources in a very similar interactive way. Once you come to the point that you're not just doing more or less interactive work with GPUs and trainings, but you, for example, want to run a larger number of trainings in parallel, want to do multi-node computations, runs that take several days, several weeks, very large trainings, then we recommend you to transition from using the Jupyter Hub and Jupyter notebooks over to the more traditional way of using HPC systems via the command line and the scheduler. Because then the automation that you can reach with that is very, very helpful in automating, like if you want to have hundreds of data sets and have to run individual trainings, you don't actually want to do that via a Jupyter notebook, but you want to automatize that in a Bash script or Python script via the command line. So how does that look like? Nick already teased you a little bit how a compute job looks like. So here on the right, the slide, you can again see the example. First, you specify the kind of resources you would like to have, and then similarly to how you would run it via command line, if you're already used to that, you just type your commands in the job script, submit it, and then execute it. And the concept, as Nick already pointed out, of a job script is that you define what to do in terms of bash commands, the required resources, and that together is then submitted to the scheduler and executed at the suitable time. The advantages of that are you can use, since it's running on the HPC system, the large and fast storage and the full resources, and most importantly, the automation. You can, instead of just running one notebook, you can submit hundreds or even thousands of these jobs in parallel, and they can be submitted in parallel on all the compute resources that are available, which makes it a very powerful concept for automation, for example, for hyperparameter studies or other things where you have to replicate a similar task several times and run it in parallel. Although that might look a little bit complicated at first, it's very, very powerful. And we as the HPC centers also offer training, even starting with Linux introduction courses, if you're not that familiar with the shell, to get you started into writing a bash script and a job script to make use of this automation feature if you need to. But there's still the possibility of using the Jupyter notebooks without needing to write job scripts. So as Nick already pointed out and explained in some detail, you log in with your laptop or desktop computer, either via SSH, as Nick pointed out, or into the Jupyter Hub as a web service from the HPC system. There you either start your Jupyter notebook on the compute nodes or submit your job script. Both are scheduled and then run on the compute nodes. So I'm going to keep that short. In addition to the traditional way of using SSH to log into a compute node, you can also, some HPC systems offer remote desktop solutions. Remote desktop means that in your web browser or in the client application, you basically get a desktop view of a virtual system, like I'm showing here. We often use that, for example, in quantum chemistry, if you want to look at the molecule that comes out of your calculation. It's easiest to just look at it visually instead of the numerical coordinates. And then these remote desktop solutions can be really helpful because you can just, on the HPC system, start a graphical application and see the graphical application in your web browser, essentially. And you can also use that for other purposes, in addition to SSH and Jupyter notebooks. Right. To sum up, basically, we see the 3 steps. First of all, if you're currently doing AI or machine learning research on your laptop or workstation, first consider Jupyter notebooks to make use of the HPC resources in an interactive and easy to use way. And once you need larger data sets, multi-GPU, long-running jobs, then we recommend to consider using it via the command line or the scheduler. Since you know which ways there are to use an HPC system, you might ask the question, yeah, what about software? So which software can I use on the HPC system, which is available, where there might be issues, and there I can say that basically all of the AI machine learning frameworks that you might be interested in are pre-installed on basically all of the HPC systems. Here's just a short list of the more famous ones: TensorFlow, Keras, PyTorch, JAX, scikit-learn, and many more. If they're not yet installed, simply ask the system admins via the support contacts to install them for you, and we'd be happy to do that. Also, have a look at the online software documentation of the HPC systems, where you can find also examples on how to use the software, what to maybe pay attention to in terms of, for example, running multi-GPU trainings with PyTorch or similar things. In these online documentations of these individual HPC systems, you can also find a lot of example job scripts that you can just copy and just modify them slightly to run your workload. The second question in terms of containers that we often, in terms of software that we often get is containers. And there I have 2 messages. On the one side, the message that Docker containers, as you might be used to running them, are not directly possible due to security issues in the shared environment with Docker. However, you can still run those Docker containers, just not with Docker underneath, but with different solutions underneath, namely, for example, Singularity or Aptainer or uDocker, which is essentially just a different driver underneath that's not Docker, but you can still run the same containers. And you can see that very easily here with the example commands that I've written down. So in order to run here the latest PyTorch Docker container with Singularity on an HPC system, you simply pull this PyTorch container into a local Singularity container or Aptainer container and run it. And there's basically no difference. So don't be scared if the HPC system admin tells you Docker is not possible. There are very helpful other solutions like Singularity or Aptainer where I can achieve exactly the same and which will work very reliably. To summarize, let me give you a short overview on the use cases that you might have and the ways that we would recommend how to realize them on an HPC system. So here in this short table on the left side, you can see different use cases from interactive use, visualization, data analysis, and so on to large parallel jobs. And especially things like interactive use, short experiments, visualizing data, analyzing data. There we recommend to use interactive Jupyter notebooks via the Jupyter Hub services that we offer on basically all of our HPC systems, which make the use very interactive, and it's just a very small step from a local Jupyter notebook use to use these Jupyter notebooks on our HPC systems. once you go to large parallel jobs, long-running trainings, production calculations, parameter studies over where you have hundreds or thousands of parallel calculations, then we actually recommend to have a look into the more traditional way of using HPC systems via SSH and job scripts, because the automation possible there can easily offset the barrier that there is to get used to doing things this way. So that's already the end of my part, basically trying to give you an overview that the traditional way of using HPC systems is not the only one, but in addition, we have Jupyter hubs, we have remote desktop services. And if you have a workload that we can't utilize one of those existing ways, we are always happy and open to explore new ways of using our HPC systems for new workloads.
So hello everyone. So I'm just gonna give you a short overview of how what are the support offers that we offer for the users of our systems and how you can get in touch with us. So the questions could be something like, hey, I can't find this version of PyTorch on the system, or it could be like Robert mentioned previously, like, hey, I have 10 terabytes of data. What is the best way to get this on the system? So oops. Yeah. So we offer support to the users on topics of AI and HPC. Apart from this, we also offer some consulting. I'm going to show you later how this works. And also we have a Q&A session that is basically this hour. So every Thursday, 2 to 3, where you could then just drop by and then ask your questions. So there's like members from different centers here who could then help you out or point you in the right direction. So how does the support structure look like at the GCS? So we have all this. So we have like documentations hosted at each of our websites. So there's one at HLRS in Stuttgart, the Jülich and LAZ in Munich. So you could like how to get so you could have a look at this and then find out how you can get your stuff running. So with some basics and also how you can apply for access on our systems. Also, we have this ticket system where you can then log in and then raise the issue, and then it's going to be directed to one of the members at the center. And we also have this HPC service desk and service portal. So just to show you how it looks, for example, on the Stuttgart, so you go to this website, HLRS for users, trouble ticket submission. And so, yeah, for users, and then trouble ticket submission form. And so you get this sort of nice page where you can then enter some details about yourselves and write a short report on what's the issue you're facing and if in case you have some attachments. And this is then sent to the ticket desk, and then they'll have a look and then they forward it to the concerned colleagues. So at Jülich, it's the same. So you have this Jülich user support, and there is this email ID, and so you can then just write an email about your issues, and it's forwarded. So at the NHR level, so things are a bit more centralized, I would say. So there's also this level 1 support of ticketing system, and there are also offers of mentoring and also some domain-specific consultations being offered. So for the user and application support, you can take a look, visit this link, and then follow the steps. And also there is a special section for AI on supercomputers. So for the ticket like the level 1 that I mentioned previously, the ticketing system. So if you go to this website, so there's different centers and then the links that you would have to follow. So let's say you're a user at the Erlangen cluster, then you just follow the link for the NHR at FAU. And so you get this page where there is this email address mentioned, and you can then just write an email regarding your issues. Also, so NHR has this nice, so different centers focus on different domains. So if you're working in some chemistry problems and then you have some issues, so you can then contact directly the colleagues at Erlangen, and then if it's Earth system, then KIT and so on. So apart from this, there are also some other partners involved in so user support. So there are 12 universities in Nordrhein-Westfalen who offer support for the HPC users. So you can find more details in this link here. And also there are contacts at this partner universities so that you can get some local support directly at the compute centers. And if you cannot then you can, if you cannot go by, then you can also write an email to the help desk and get your queries resolved. So apart from this, both GCS and NHR all have quite some experience in making HPC energy efficient. And this is also since energy consumption is a topic of concern frequently. So this knowledge is also going to be leveraged to kind of make AI workloads more energy efficient and yeah, try to reduce the energy consumption on this regard. So apart from all these ticketing systems, we also offer different trainings, workshops on multiple topics. So again, this could be a simple introduction to Shell or introduction to using PyTorch, or even how to set up multi-GPU workflows or how to run multi-node workflows. So you can on the NHR website, this is under the section AI events. Also GCS has this trainings and workshop section, and there is this Gauss Alliance calendar where you can then find all the events based on the calendar. So I'll show you quickly. So this is the Gauss Alliance calendar. So the link is here. You can so you get this nice overview of the different available trainings on each day. So today there is methods of AutoML and how to utilize them at one of the NHR centers. So you can also enter the title of the topic that you're looking for, so machine learning or AI, deep learning, Linux, and so on. And you get this filtered list of trainings on that topic. So yeah, again, we offer, like I mentioned earlier, there is a weekly Q&A session on Thursdays from 2 to 3. So it's you would see most of the colleagues who are here. We would then be there also, and you can then just drop by, ask your questions, and then get it either cleared, or then you find out whom you should take this to, and yeah, get it resolved. And you could also mail at this mail ID in case you have some questions.
So I have now the fun to actually talk you to the different sites and systems that are available. And I try to do it in a somewhat entertaining way, and because in principle, it's the differences in hardware I'm going to present here. So we've already had some insight into the big centers. So we will now start with the tier 2 centers. So which is basically Let's start with Aachen. There we have basically a machine that consists of nodes, 52 nodes at the moment, that have basically for NVIDIA H100 each, with substantial amounts of memory. So if you rely on NVIDIA, if your framework works best there, that's potentially one option to go. In Darmstadt, we have more hybrid availability of systems. So we still have a few V100s, but also A100s with different mappings. So different numbers of GPUs per compute node. That is sometimes important, and different amounts of memory per each GPU. When we look at VAU, at Erlangen, there we also see that we have a somewhat more inhomogeneous offer. So we have basically A100s, but with different amounts of memory. So that might be also beneficial to you. We don't have yet H100s. If we switch to Göttingen, there we also see primarily NVIDIA hardware, so A100s and V100s, but also a few H100s, so the more recent NVIDIA GPUs. And well, with KIT, we also have an NVIDIA side mostly, and but homogeneous this time, so they really have a lot of such A100s with reasonable amount of memory, 40 gigabytes. And now let's come to my side, so to University of Dresden. So we have a rather new installation of lots of H100s with large amounts of memory, but we also still have a substantial amount of A100s, NVIDIA A100s with not so much memory. And well, if you for some reason need still V100s in a Power 9 infrastructure, I think you have not too much time left to actually use this, because it will turn off anytime soon, which is why it is already grayed out here. And of course, we also have a big CPU cluster if you need, and some of you probably do, just CPU training time. Not all the models, especially the smaller models, do not always scale well with GPUs. So sometimes it's also beneficial to stick to CPU clusters. By the way, all the centers here also have typically CPU clusters. It's just that they are not on this list. Good. When we talk, and now it's actually getting more interesting from a hardware point of view, because we have different types of GPUs now. If we look at ZIP, we actually see Intel GPUs. So if for some reason you are familiar with Intel GPUs and would like to work on this kind of hardware, then you're good to go and apply there. But they also have A100s if you, well, live well with NVIDIA infrastructure. When we look at Paderborn, there we have basically NVIDIA hardware again in different flavors, substantial amounts of A100s with large amounts of memory, but also the older A100s and A40s. If we look at NHR at Südwest, there we basically have, again, slightly different hardware. And if you would love to work on AMD GPUs, because that's working well for you, then you're good to go there and apply for resources at Goethe HLR. And they also, if you are close by to the site and familiar with it, of course, they also have NVIDIA A100 hardware. Good. So basically, and I think we've already seen that today, basically all the systems have direct liquid cooling. So that has positive influence on the power usage and the, well, reasonable costs that are needed for doing the cooling. So I don't want to spend too much time on that. That's a bit tricky for me because Slides. And yeah, well, I asked for, because you've seen that all those systems are more or less not identical, but similar. Therefore, I asked the centers to also provide some special features of their systems. And Aachen was so kind to actually add what makes them unique, or what is something that is different compared to other sites. So let's start. So they have apparently. You want to say that, John?
Should I take over just for
Yeah, I
this
think that makes more
slide?
sense. Yes,
Yeah,
it's your slide. Go ahead, please.
Yeah. So I think most of the things that that are on the slide here are actually not quite unique to Aachen, but are available on all the other sites. Like the Jupyter Hub, which Robert already said is available on most or all sites. What we also have in Aachen is an interactive login node with H100 GPUs. I think this will also be the case with most sites. But this is a very nice feature to use, because it allows you to work also interactively on the login nodes without being too much charged for it with computing time, if you're even charged. Also, software-wise, as Robert said, this is also very similar with all the sites, the frameworks which are available. At our site, it's also possible to run your own Aptena containers. So, or you can even have configured them on the HPC site. This is something that is not possible at all HPC sites. And we also have some selected few data sets. And the question of which data sets are available at each specific site depends. Yeah, it's site specific. So I would say most of it is. I would say from what I've seen today is that most of it is rather homogeneous across the sites.
Okay, thank you. I think it's nevertheless important to point this out once more, because I mean, just the list of hardware is not very meaningful unless you really depend on certain architectures regarding the GPU or software. And I think this is the way you interface with the hardware is actually also important to know, although more or less the flavors are there, but it's important to tell them. Good. Okay, so how do you apply for GCS and NHR resources? So how do you get access to the system? What do you have to do? Well, there are two sites. I will start with the NHR, which is one site. And at the NHR webpage, there is a portal that can be accessed via this particular link here. And there you can apply for so-called NHR starter projects. And the goal of those projects is actually to give you as easy as possible initial access to resources. So it's fairly simple to submit a successful proposal. Thereafter, for normal or large projects, but your easiest way to get access is really to use this NHR starter, because there's no need for experience with application procedures at NHR, no HPC knowledge, and you also will not be asked many complicated questions in this application project. You don't have to apply, you don't have to write down a complex proposal justifying why you need all those resources. It is relatively easy to, well, it's very easy to actually apply for it, and you will quickly get an answer. That's the most important part. The NHR basically that is going to be selected can be highly influenced by yourself. So you can basically ask for a certain center or name a certain topic. Then the NHR representatives will think about your demand and basically give you the center that fits best to your topic. And basically you can use those resources, and by the way, they are free of charge for scientists all around German universities and research institutions. And when you make your experience with that, you can actually, while you are still computing and gaining more experience, can apply for more resources if that turns out to be needed. And those classes would then be normal or larger projects with millions of CPU and GPU hours if needed. Two different things. When we talk about NHR, this kind of category, so this project you would apply first for is called starter project. In the GCS context, they typically refer to what can be seen as development context. So that's basically their smallest category of project you can apply for. When it comes to NHR, you should basically, your PI, so the person that is going to ask for the resources, should at least have a PhD degree. That's a formal requirement. I didn't make this up, so I can't really comment on that, but that's a requirement. You basically briefly provide some information, like in an abstract, about your project, and you will be asked to a very small extent, actually, on the types of CPUs and GPUs that you need, the center that you would like to work in, and yeah, what kind of simulation are you using? What is your AI approach? And that's pretty much it, I would say. So that's a very simple way to get access initially. When it comes to GCS, as I said, it's a slightly different approach. There you have a different web page, and it is not called starter project, but it's actually called preparatory access. Or in this description, you will also find the word development, which is why we call them development project. But in the end, they also have a website. Basically, that works like the NHR approach as well. So you have to specify a PI and probably a person of contact if the PI is not sufficient. You basically provide a brief abstract of your goals and what you want to achieve, and a few more things. And with that, you are also typically good to go within a short amount of time, which is the idea of that. And if you need more resources, once you gained access to the machine, you can always ask for that and apply for it on the same page, in a sense. Good. I think I mostly said all this already. And yeah, this is pretty much identical to NHR. You basically finalize your submission. Important things is you can typically, and I think that is true for both sides, for both application portals, you can typically just start your application. And when it turns out that something is still missing, you just save it so you don't have to start over again. And you can then just later on continue. And once you really finalized all the things, or the few things that need to be finalized, you can just submit it and get the chance to sign it, and will get an answer pretty quickly for this kind of category. Okay, one important thing I forgot, because the large and the normal project sizes, they are typically reviewed not on a daily basis, but rather a weekly or a monthly basis. But for the starter projects, this is not true. So there is a higher frequency of basically answering those requests. So you don't have to wait for much time in order to get resources granted.